Last week, we talked about image data, specifically how image data could be stored. We viewed a very simplified version of image data, specifically with just two different kinds of colors, white and black. But to express a specific portion of the image, you use a pixel. So a pixel is the smallest unit of an image. It is the smallest visual unit, I guess. So for the smallest thing that you could see. A pixel expresses one color and one little, I guess, box, one little square of your picture overall. The more pixels you have, typically the better, because you're able to show a better, less blocky image, so less pixelated image. I mean, it just looks more realistic, if you will. What we use as our example is a very pixelated black and white image where we use 0 to express black pixels and 1 to express white pixels. When storing the data, we did data, that is a fact. But more importantly, not more importantly, just as importantly, we had metadata accompanying it. So right here, for example, the width and the height. The width and the height are not the data, is not the data itself. Metadata, if you remember, is data about the data. The data is this image. Metadata, so you want to, or what else provides more information about your data, is the width and the height in our case. So here we have our example of a very simplified image. Now the question is, what happens if you have other colors that you want to represent? Like these. There's two main color models that we use. You guys might recognize this one right here, RGB. You guys might have heard of RGB before, especially if some of you guys have taken HTML and Java and you guys are used to creating your own figures and your own drawings and images. You use RGB to choose the color of what you intend a shape to be. CMYK, this is not used too much in a computer per se. So for example, your screen most likely is using the RGB format. CMYK though, this is normally used in printers. If you guys have a printer at home and you guys open the printer to look at the ink cartridges, these are the 4 colors that you will see inside of your printer. C for cyan, M for magenta, Y for yellow, and K is actually for black. You would think that it would be B, but it's black. So how we express a specific color or how we create a color is it's kind of like a layering. So if you put more cyan, let's say you decide to put more cyan in, actually maybe I think I have the next slide. Oh, here we go. So depending on how you mix the colors and how much of a specific color you add in or you leave out, this will create a specific color for you. So if we take a look at this red color, this is made up of magenta and yellow. No cyan and no black was added in this color. To get a perfect magenta color, you could see you add just magenta, 100% magenta. Whereas you leave the cyan, and you leave the yellow and black out. You could see for yellow, 100% yellow, no cyan, no magenta, no black to get this yellow color. Here's a cyan color, just cyan would give you just 100% cyan, nothing of anything else. So this is what we call a subtractive model. We call this a subtractive model because if you take a look, the color of the paper and black is the combination of all colors. So if you combine, I don't know, oops, there we go. all, if you look inside like our little Venn diagram looking thing, the combination of all colors, magenta, cyan, and yellow will give you the color black. Whereas RGB, when you add all the colors, it'll give you white. This is what we call an additive color model. So if you think about it like this, if you have nothing, so for a subtractive model, if you have no colors, then you have white. That's the reason why it's a subtractive model, because if the colors that you remove, you get a white base. Whereas for RGB, if you want white, you have to add all the colors in, which is why we call it an additive color model. Let me take this. So subtractive model, because you want white, you must remove all the colors. Whereas for an additive model, if you want white, you need to add all the colors. All colors, meaning your three colors, R, G, and B. So red, green, and blue. Typically, what you will use is this one right here. Once again, RGB is used mostly for images. It is used mostly for our screens. So pretty much almost everything that has a pixel, we will use RGB for. CMYK is also used. However, I would say it has a very specific niche if you want to use it for images. But more importantly, it's more common in printers. Just know both of them just in case, but of the two, RGB is definitely more important for the purposes of this class. So let's go dive into RGB a little bit more. We talked about CMYK a little bit. We normally use the percentage of each color, but for RGB uses 1 byte to represent each color. How much is 1 byte? How many bits is 1 byte? Anyone remember? Should I do a poll? Oh, perfect, 8 bits, thank you. It is 8 bits. If you don't remember this, if you're taking the AP test, get it in right now. It is 8 bits. So, what's the largest number? What is the largest decimal number that can be represented with 8 bits? Does anyone know this one? So you have 8 bits, and the largest number you want to represent with 8, or the largest, let me actually clarify this, the largest decimal number. Because obviously, thank you, it is 255. The largest binary number that we can get is 1111111. That's the largest binary number you can have when you have 8 bits available. So when we do the addition, so 2 to the 0, 2 to the first, 2 to the second, 2 to the third, plus 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh, this results in 255. That means this is the largest decimal number that can be used to describe your color. 1 byte is used to represent each color being RGB. So that means each pixel is 3 bytes of data. 3 bytes because you have 3 colors. So 3 bytes, you have 3 colors, R, G, and B. R for red, G for green, and B for blue. Each color is 1 byte. That means each color is 8 bits. Each 8-bit set can give you a maximum number of 255. So kind of like CMYK, where we use percentages to express the color that we use. So like here we say like, oh, this is 100%. That means like you're using only like all of like the brightest that cyan could be, like the strongest concentration of cyan, or this would be the strongest concentration of magenta. This would be a toned down version of cyan. So like not as bright as cyan can be, but you're just removing some of cyan. You only use 50% of it. We use the concept to this, but instead of doing it by percentages, we use it on a scale of 0 to 255. Zero means there is a lack of that color. If you have R is 0, that means you have no red in it. But if you have G is 255, that is the strongest that green could be, 255. So that is how this representation will work, as opposed to percentages, which is what the CMYK model uses. The RGB model will use is a little bit more closer, or is a little bit closer, more closer, a little bit more close. Yeah, English. It's closer to a computer, like a computer architecture where you use binary numbers. So let's take a look at how RGB works. So as you can see, the smallest value that R, G, and B could be is 0. So we have a few zeros scattered around here and there. So we can see the 0 here, 0 here, and then 255. This is the highest value that one of the colors could be. So this means this row right here means you're only using red and you're not using any of the other color values. You can mix it up too. So like, for example, whoa, calm down. So right here, we look at this version of purple. We have 68, 10, and 127. So out of this, on the scale of 0 to 255, we use the value 68 to indicate the strength of red out of 255, only 10 out of 255, and then 127 out of 255. This implies that there will be more blue than other colors. So this is how it works. Let's do a more hands-on version of this, where we're going to do, let me share this part. Do you guys remember this? Did you guys do this for homework? Okay. So this time, however, we are going to do a color version of what we have, as opposed to a just black and white. So for image width, let's do let's say we're going to do 3 by 2, or 2 by 3. So we're going to have a width of 3 and a height of 2. So let's take a look at our metadata right now. This one here, the very top row, indicates the width. 0, 0, 0, 0, 0, 0, 1, 1, 3. This is the same thing as 3. So this is our metadata for the height. The one below that, right here, next byte, 0, 0, 0, 0, 0, 0, 1, 0. This is 1 byte, which represents a decimal number of 2. This indicates our height. And then finally, we have this one here. In the previous exercises, where we were only doing 2 colors, black and white, you didn't have this for metadata. The only 2 things that were being stored as metadata was the width and the height. This time we have an additional one. This represents the bits per pixel. If you recall from the PowerPoint, which I just stopped sharing so I could share this, each pixel has 3 bytes. 1 byte dedicated for the red color, 1 byte dedicated for the blue color, and 1 byte dedicated for the green color. I did that out of order, but RGB. So how many bits do we need? We have 3 bytes. How many bits? Very good, 24 bits. So 24. Now we can see how the pixel format looks. The first 8 bits, meaning the first byte, is for the red. The second byte, or the second set of 8 bits, is for the green, and the last one is for the blue. So each set of 24 bits is 1 pixel to show us what color that we want. So let's say I want just pure red. I don't want any other color. That means I want the red to be, let's just say I want like just pure, like the highest amount or the highest value of red possible. What would that number be as a binary number, considering that you have 8 bits? Right, you would have to 1, 1, 1, 1. So 1, 1, 1, 1, 1, 1, 1, 1. That would be your red. Right now it's not showing up because we don't have a complete set of 24 bits to represent our pixel yet, but we'll get there. What about green? If I want a lack of green, an absence of green, what would I write for this particular pixel? So for green, what would it be? Perfect. We want zeros all across. And then what about for blue? If we don't want any blue, we want an absence of blue in this pixel, what should it be? Yes, very good. It's the same exact thing. And we have our first pixel, this red color right here, this vibrant red, because we have our, this is just how we modeled it to be. So if I want to do only green, so there's a bright, vibrant green, and I don't want any other colors, I would do red as just 0, green as the maximum green color, and blue as nothing. And if I wanted the dark blue, like the most vibrant dark like blue that I can get, I would do zeros for red and green, and then this blue. So these are the RGB colors separately. If you guys remember our, actually, let me start sharing again. Let me share this. Now, if you remember our additive color model, you can see that where certain things overlap, we could get different colors. So if we mix, according to this, if we mix red and green, we will get yellow. If we mix blue and green, we will get cyan. If we mix red and blue, we will get this magenta, purple, really vibrant magenta color. If we mix all of them, we should get white. So let's try mixing some of these colors now. Let's try to get yellow. So yellow was a combination of red and green. So let's just try to make the brightest yellow possible, meaning we're going to jack up the RGB values for R and G, because like the red and the green, red plus green gives you yellow, according to our additive color model. So for R, we're going to give it the full value. G, we give it the full value. We don't want blue in this, otherwise we wouldn't get yellow. And there's our yellow. You might have also noticed that if we mix all of the colors together, we get white. So full on colors for all of them, we get our white color. So what do you think is going to happen when I do zeros for everything? What do you think is going to happen if I just do zeros, like 0 for red, 0 for green, and 0 for blue? What do you guys think? Well, very good. We got black. So this is the reason why it's called the additive color, the additive color model. White is the combination of all colors. Black is the absence of colors, which makes sense. If you guys are taking physics and you guys have learned about this, this definitely makes sense. But if not, it's okay. You guys will get there if you do decide to take physics in the future. Let's see. With me, I'm afraid that it's going to change. Yes, it is. So there we go. Let's see if we try to change things up a little bit more. Let's say I decide to, instead of using full on like just ones only and zeros only, I kind of mix it up a little bit more. So let's say I want, actually, maybe I could show you guys this. Let's see. If you guys just Google like RGB color picker, you should be able to see like if you go across the RGB values for each of these. So let's say I like, what do I like? What color do I feel like doing today? Let's see. Let's say I want this color because I like pink. So I have 242, 208, and 237. I'm going to, this is the RGB color that you guys can see here. 242, 208, 237. I'm going to convert this into my into binary numbers and then go ahead and write it in. Because I am running out of time, I'm just going to give you guys those binary values. But 242 as a binary number is going to be 1111 0010. So this is the R value. So R is 242. This is the binary value 1111 0010. And then after that, we have 208 for our green value. So as our green value, because once again, I don't have time to convert it with you guys, 1101 000. My keyboard just died. 000. And then I have 237, which is our last color. So, or for blue. So that means for blue is going to be 1110 1101. And you can see that pink color, oh, it's kind of a little bit too close to the absence, like this like null color. But you can see that that's how we develop our colors and how colors are being stored as pixels, or how color data is being stored for pixels. There's also a hexadecimal version. So I don't know what's going to happen if I click hexadecimal. Let's just go ahead and copy this just in case. Ah, nice. So there's also, it could be stored as a hexadecimal, or it could not really stored, but rather you can change your binary representation into a hexadecimal representation, because hexadecimal is frankly easier to read than a binary representation. For binary, there's so many numbers, like 1 0 0 0 1 1 1. Like it's very difficult to just look at a number and just know what number it's supposed to be. So we could convert it into hexadecimal. So if we see here, this is the hexadecimal encoding, F2. So that the first two, these first two represent the red color. The second two hexadecimal digits, D0, represent the green, and the ED represent the last color, blue. So if I decide to do a different color, let's see, what have I not done yet? I guess I haven't done like a purple. We'll do a like this vibrant purple. I can copy and paste this hexadecimal code. Keyboard is dead, I forgot. And we can see that color here that represents our purple pixel. Any questions? Everyone's okay so far? So let's go ahead and quickly wrap up our unit on data then. So we also, last time we talked about lossy versus lossless compression. Just a quick summary. Lossy means that you are losing data. You are purposely throwing out data in order to compress your data, meaning to make your data size, your file size smaller. Um, Oftentimes you want to do it to the point where it's still not noticeable. When you take a look at these three images, the original 50% lossy compression and 80% lossy compression. At first glance, they look pretty much identical, but upon zooming in, you tend to be able to see the difference between these. In fact, comparing the two, or the comparing where I circled, the original JPEG file is pretty nice. It's just, you don't see pixelation. But on the 80% lossy compression file, you do start to see some kind of pixelation going on. It's not a big deal unless you really closely analyze it, but oftentimes this is just enough to get the job done. The lossless compression, which is where you don't lose any detail. And normally you want to do this by finding patterns in the data. And we did an example with the tongue twister, how much wood if the woodchuck could chuck wood, or chop wood, I don't know. Chop, we'll say that. And we talked about grouping words together, replace words. That way, instead of having a result with as much text data that you would have to store, in this case 58, we reduced it to 20. So that was lossless compression. So the reason why lossless image compression works well most of the time is because the human eye isn't very well trained to be able to make big distinctions between colors that are very similar. So if you take a look at these two colors, they're actually different, as you can see by their RGB values. So on the left-hand side, we have an RGB code of 25, 32, and 132, whereas the RGB value on the right-hand side is 25, 35, and 120. These two are different colors, but you probably wouldn't be able to tell that. So what lossless compression will do is throw out one of these colors and group whatever colors they have to be one, like decide to throw out this one. It will change all of these colors, this color instead. That way you don't have to store as much color data as you had to, which is why we see some kind of pixelation going on when we do lossy compression. That's because the colors here in the original JPEG, they were every single pixel's color data was being stored. In the 80% lossy compression image, it's starting to group those colors. It's starting to group them, and those that are very similar to each other will just become one of the same color. Which is why when you zoom out, you don't see the difference, but when you zoom in, you can see how blocky it could be, because those colors around it have just become one color as opposed to multiple different colors. Oops. Did not mean to do that. So a couple concerns that come from data and information. So first of all, the security of your data. So we will be talking about, just leading up to our next unit about the internet. When it comes to the security of your data, a lot of you guys store your data on Google Drive, probably. You guys all have emails, everything that you have on the computer, or even what you store on the internet, on the cloud, is data. So security is always going to be an issue. Is someone trying to have unethical access to your data? You always want to have good security, have a good password. So be sure. Privacy, digital footprints and fingerprints. So know what this means. So digital footprints or fingerprints, they're both the same thing. It's trail of little pieces of data that we leave behind as a sign of our presence as we go through our daily life. More on this when we go. When we provide personal image sites to gain access or privileges, our data is stored and may be sold with or without our knowledge, which is a big ethical issue and a big ethical debate that is going on in society. When you are on the internet, or when you like sign up, when you create an account, you always submit your email, you always submit your date of birth, your name, your last name, sometimes your actual address or your phone number. What happens to that data? What is it used for? Oftentimes it's not clear to us as the user. And because of that, a lot of policies are being recommended and some have been implemented. We'll be going over that there as well. Look forward to it. That's all I have for today in terms of data. Next week, we'll be talking about the internet, how the internet was formed, and the basics of how the internet works.